let's go ahead and get started then. So we do have a couple of problems here of varying levels of goofiness. We're going to start on the lower end, and then we're going to work our way up to what I would consider to be the very pinnacle of what we kind of do with our integration techniques so far. This is not an easy one. Anyway, let's go ahead and get started on that one. So we do have a rational function, a polynomial divided by another polynomial. The degree of my denominator is 4, right? Highest power of x, and the denominator is 4. And the degree of my numerator is for a constant function, so that is degree 0. Right? So the degree of the denominator is definitely bigger than the degree of the numerator. We should be thinking of partial fractions here. And as we're going to go do partial fraction decomposition, we have a little bit of work that we need to do with this denominator. We need to factor this denominator as much as we can. So what is the most amounts of stuff that I can sort of factor out from x squared next to x squared, x squared? And we got x squared, and we have 1 plus x squared, no parentheses around that square. This square is only on that x. And we are left with the remaining question of, can you factor 1 plus x squared? Yes. Yes. All right, what are the factors?
You get one out of it.
Cool.
Does
Any
not.
proper factors?
Nope.
We could pull out a 1, but we kind of want like meaningful factors. And there is sort of, I suppose, a little bit of review from algebra. Here it's not so bad to tell that this thing isn't factorable, because if we try and solve this thing equal to 0, we're going to get plus or minus 5 shown up, and that's no good right for you. Other things to check. In the case of, is this quadratic factorable? Everybody remembers their discriminant? It's the stuff underneath the square root in the quadratic. And so b squared minus 4ac. If b squared minus 4ac is positive, we're taking the square root of a positive number. That's well defined. We're going to get 2 roots. This thing is factorable. If b squared minus 4ac equals 0, we're taking the square root of 0, which is what? Root of 0? Yeah. No. 0? 0. We're going to get 0. We're only going to get 1 root here, so which means we're going to get a repeated linear factor. If this thing is negative, however, then we're going to get the square root of a negative number. That's not good. So if this thing is less than 0, then the quadratic is not factorable. Here in this case, a is 1, c is 1, b is 0, so we're going to get negative 4 times 1 times 1. Negative 4. It's not factorable. Which means this thing is as factored as it can be. We got 2 things going on here. We have an irreducible quadratic. Nope.
No.
We're still doing partial fractions on that. And then we have a repeated linear factor. Now, I think last week, Wednesday, I mentioned what to do with an irreducible quadratic when you're sort of writing out your trial partial fraction decomposition. I don't think I mentioned what to do when you have a repeated linear factor. Right, we're sort of trying to undo fraction addition, and we're treating each of the individual factors that are going on in the denominator as something that could have potentially shown up in the thing that we were asked to add together. And in the case of a repeated linear factor, you could have something divided by x show up in the original kind of undone problem. You could have something over x squared. You have two different fractions using either x or x squared. So you kind of have to treat the repeated linear factors sort of separately in that case. So again, a constant over x, and then another constant over x squared. Just because we don't know what showed up in the original formulation before we added these fractions together. It could have just been one of them. It could have been both of them. You don't really know. It's sort of the point of partial fractions is to find out. And then last one, we got the irreducible quadratic. And for a numerator for those things, we don't use a constant, we use a linear.
So C of X.
Yeah, c times x plus.
I'm trying to follow. I'll get there.
Right, when we're dealing with linear factors above linear, we put constant. Right, when we're dealing with irreducible quadratics, we put a linear on top. We always reduce the degree by one and we put that linear on top. So this is degree 2, reduce it by 1, degree 1, it's a linear.
So from what I'm understanding, we're treating this as almost two separate fractions, with 1 over x squared, and that will break down into a over x plus b over x squared.
Yeah. This repeated linear gets broken up into those.
Yeah, I'm just trying to remember how when those two would come together would equal x 1 over x squared. Does that make sense? Like we're supposedly undoing this? Yeah. Like how we did it on Wednesday?
Yeah.
But that should work both ways where you can redo it. I'm just, my brain isn't redoing it in the correct order. So like a over x plus b over x squared doesn't come back to something over x squared to me. I don't know.
Something over x squared.
They don't come back to 1 over x squared.
And so I suppose part of the could be facing is once we do figure out a bunch of these things, and when we multiply fractions, I could multiply top and bottom. Get some because we don't know, at least for the moment, that that's a potential thing that could have happened. We have to account for it. Yeah,
So 1,000 x cubed out front in the original.
yeah, and then it'll be a over x plus b over x squared plus c over x cubed. Okay. Then I have one thing to show the powers lines for each of the powers of that linear factor. But we're now at that point where we kind of follow through partial fraction decomposition strategy of multiplying multiply both sides by the denominators all multiplied together to cancel them out, set up a linear system, and solve that linear system. So let's clear the denominators. So on the left, we're gonna get 1. On the right, we're gonna get a times x times 1 plus x squared. Only one of the x's will cancel. And then we're gonna get b times 1 plus x squared. We have x squared here, x squared there. Those are gonna cancel. And then we have cx plus d times x squared, because the 1 plus x squared cancel. Okay, so far? Solomon doing all right? Yeah. Okay. Erica doing okay?
Yes, I'm doing great.
So let's multiply all this stuff out, set our coefficients equal to each other. So ax times 1 is ax plus ax cubed, ax times x squared, plus b plus bx squared, plus cx cubed plus dx squared. Equate coefficients. On the left here, what's the coefficient of my x cubed? 0. And then over here on the right, I got an x cubed term there and an x cubed term there. So 0's got to be a plus c. Now I got x squared. What's the coefficient of x squared over here? 0. And x squared is here and here. So b plus b. And then coefficient on my x term over here on the left, 0. And we only have a there. That looks like it's easy. Hopefully that looks a little more good. Okay. And then last one, constant term. What's my constant over here on the left? 1. And only one constant over here. We have a linear system in front of us. I have, at least I hope, made it very clear that I do not care how you solve this linear system, as long as whatever you're doing is technically correct. So you could set up a matrix to solve this thing. You could set up direct substitutions and back subs to solve this thing. You could do elementary row operations if you use a calculator. I'm kind of looking at this thing going, it might be easier just to start plugging some numbers in.
A is 0.
Yeah, A is 0 and B is 1. That's really nice to have from the get-go. So let's go ahead and plug in A being 0 and B being 1. 0 is equal to 0 plus C, and 0 is equal to 1 plus D. 0.
So where did we get the equal to zeros again? Can you explain that part to me?
Yeah, so we're equating coefficients. So I have over here on the right like x squareds and x's and x cubes. Over here, might technically have x squareds and x cubes and x's, but they're not sort of written, right? And this is due to the fact that their coefficients happen to be 0.
Okay.
And because they're 0, or their coefficients are 0, those terms go to 0 and 0 plus something like that. So we're lazy in economics. But that is what we're doing, is we're equating the coefficients. Yeah, Erica?
Never mind, I'll wait till.
You're good?
Yeah.
Alright. Alright, so we got B is 1, A is 0, C is 0, D is -1. Let's plug all of those things back in up here and get our decomposition. So let's see here, A is 0, B is what, 1? And C is 0, D is -1. So we'll just make that a minus. So as we go to integrate this thing, we integrate that thing instead.
No.
And depending on your memory of derivatives, oops, plus something here. These could be very, very easy. What's my antiderivative of 1 over x squared? Not quite. -1 over x. And remember, treat it as x to the -2 raised the power by 1 to divide. So -1 times x, or -1 over x. And then we have minus. And then I need an antiderivative of 1 over 1 plus x squared. This is one that, in theory, everybody knows right off the top of their head, right, Braylon?
Sure.
Totally. Anybody know what this one is? This is arctangent. So, I'm just gonna write arctangent. There we go.
When did we learn that?
Calc 1. This is one of those cases where back in Calc 1, in theory, you learn that the derivative of the arctangent function is 1 over 1 plus x squared. And then back in Calc 1, you did direct integration of, I see this thing's derivative, so I'm just gonna use that derivative formula back.
So is arctan tangent to the -1? Or that's something else?
I'm gonna be very kind of careful about notation here because this is something that confuses trig students and calc students. This thing and this thing are two totally different things. This is the inverse function of tangent. Over pi over 2, no, negative pi over 2 less than x, less than pi over 2. A tangent of x is a periodic function, period pi, so it repeats itself, so we set no restriction, so it passes horizontal line test, and we can take an inverse. So we get inverse function from doing like a reflection across the line of y equals x. So here, this function looks something like that-ish. where we have horizontal asymptotes at negative pi over 2 and pi over 2. This thing is cotangent. Of which I don't even remember what the graph of cotangent looks like.
Isn't just that weird?
I'm sorry?
Well, it's rotated 90 degrees
Okay.
where the x-intercepts are.
Isn't just that weird?
I'm sorry?
Well, it's rotated 90 degrees
Okay.
where the x-intercepts are different tangent and cotangent.
Yeah. The fact of reciprocating them just does weird things. Right, it's not just rotation, right? Because I do remember what sine and cosine look like, and secant and cosecant are definitely not just rotations of levels. They're like very kind of bizarre. Alright, sine looks something like that. And cosecant would look something like that. So these are two very, very different things. When it comes to like me teaching trig classes, I almost never use this notation just because of how easily it gets confused for reciprocals and negative exponentials. What's that?
This is tangent to the negative cotangent.
Cotangent, okay, sure. I usually just write my inverse trig functions with the arc instead. Make it very clear, there's no negative exponent, confusion, shenaniganry going on. This is an inverse function.
So that has nothing to do with that.
This and this are the same.
Oh, okay.
This and this are
Are
very
not.
easily confused with each other.
Okay.
And this are very, very different from each other.
Okay. Gotcha.
So when in doubt, when you're dealing with inverse trig functions, don't use the negative exponent notation, just straight on. You'll help everybody, including yourself. Let's suppose for a second that you didn't remember that this was arctangent. Right, Braylon? How would you do that then if you didn't remember? This is trig sub. If you didn't remember the direct type. You got a plus sign here, plus sign kind of looks like the letter T, right, Diego? So it's going to be a tangent substitution. And when you get done with that tangent substitution, you get arctangent. So if you didn't remember that this was arctangent, you could have passed through trig sub. So could have recognized or used trig sub. Yeah, Xavier?
If we see a derivative, we just know we can move on, or do you want us to do it?
This is where we get to like a level of trust.
Okay.
When in doubt, you can always ask. In principle, I am okay with like if you recognize this thing's anti-derivative, you can just move on. However, have I totally seen in the past of just blatant, we'll say cheating, of like blatant, I looked this thing up and I'm totally playing, I recognize that, I've totally seen that before. So we're sort of on a level of trust there when it's asked. Right, it kind of goes to like those constant multiples of inside trig exponential functions. Right, like the antiderivative of like cosine 3t or something. Right, so it's 1/3 sine 3t. Like I'm totally fine with that. Seeing the 1 over 1 plus x squared goes straight to arctangent, I'm totally fine with that too. things I probably wouldn't be super fine with, taking a look at this thing and going, oh, this is obviously -1 over x minus arctangent of x. Yeah, that's probably no good.
What about now, right?
I got a boo-boo.
No. You can check. Good? Good. Alright, let's move on to the more goofy one. We want to find the volume of the region bounded by y equals 3 over x squared plus 3x plus 2 between 0 and 1, rotated about the x-axis. It's more goofy in the sense of this is going to be like a chapter 6 question. This is the volume of rotation, which means geometry is back. You're so excited, right, Owen? So let's just get kind of a picture of what this thing might look like. Which means, I suppose, reviewing some stuff about rational functions. Down below, we do have a quadratic. We would like to factor this quadratic. X plus 2, x plus 1. And if I'm trying to sketch a graph of this particular quadratic, use my x-intercept, or my x-axis, there's my y-axis. I know a few things that are happening at x equals -2 and x equals -1. Vertical asymptotes. Other things that you may or may not remember when you're dealing with a rational function whose degree of the denominator is bigger than the numerator is that it has a horizontal asymptote at 0. In other words, as x gets really, really big or x gets really, really small and divided by bigger and bigger and bigger and bigger numbers, it's going to go to 0. I put in air quotes for the horizontal asymptote because it doesn't really behave like an asymptote, even though that's what textbooks call it. Because sort of in the middle of the graph, it's totally okay to cross through that horizontal asymptote. It's just the behavior. And last thing we're kind of doing here is just, making a quick sketch of the graph. So let's go ahead and pick a point over here to the left of -2 to plug in and get some idea of sign. So I'm going to say plug in -3. So -3 plus 2 is -1, right? And then -3 plus 1 is -2. So we have -1 times -2. What kind of number is that? Positive. You've got positive number up top divided by positive number. What kind of number is that? Positive. So over here, I'm going to be above the x-axis. And behavior says we got to come from 0. I'm going to be above the x-axis. I'm approaching a vertical tangent line, so I'm going to go up. I am now on the other side of my vertical asymptote. The degree of this linear factor is only repeated once. It's not squared or anything. So I want to re-pick up the graph on the opposite side of the vertical asymptote, on the opposite side of where I ended up top. I want to start up back down below.
So can you explain what starting down below because?
Fancy words you may not remember from algebra. Multiplicity of x plus 2 is 1, or the exponent is 1. So we want to follow sort of the same kind of behavior as 1 over x, the graph of 1 over x, and that does switch sides. Because as we go and switch sides, this factor is changing from positive to negative. So in that little calculation we did over here, and we got a positive number down below, now this is positive and that's negative. which means that one's negative. Question, am I gonna hit my x-axis here, or is there a number that I can plug into x, a real number that I can plug into x to make this thing equal to 0? No. Right, because that would involve the numerator being 0, right, denominator being 0 means vertical asymptote. If the numerator is somehow equal to 0, that means we have 3 equals 0. And that's no good, right, Solomon?
No.
Yeah. So we don't have any x-intercepts, which means we have to turn back around as we approach that vertical asymptote and go the other way. Multiplicity here is 1, so as we switch sides on the vertical asymptote, we switch sides again vertically. I ended down below, I need to start back up top. And then my end behavior is going to pick up again and I approach a little horizontal asymptote. Get a lovely little graph. How well does this match up with what your graphing calculator tells you, Xavier?
Look what my calculator said.
Invalid dimension. That's a problem. Hit second and the plus button, I think. Hit clear a few times. Press 7.
Press what? 7?
7. Yep, all around. Yep, reset. Try it again. How's it look, Xavier?
It seems to have crashed my calculator.
What?
See, no buttons work, it's just stuck here.
What?
I don't know. It's brand new, I don't know.
Man.
Go ahead.
Oh, it's still spinning.
Oh, no.
Yeah, your little loading wheel is still going.
Oh, gosh.
It did it again, mister.
Dad, I'm gonna have to take a closer look at you forgot to put your entire denominator in parentheses. Hey, there you go.
Okay, yeah.
Life is good, honey. Life is good.
Hey, there we go. That looks about right.
Oh, there it is.
This is when I try to do the matrix. Maybe I put the matrix in wrong. Where'd you get that purple one from, Solomon?
Stat plot.
Where you get that from? Because I want one. Walmart?
No, I got it from the bookstore.
The bookstore? I didn't see it.
Yeah, 'cause it's all on home.
Let's talk to the man. So wait, that came up when you tried to do. Oh, or-
My matrix, yeah.
You got your row and column number a little messed up. It should be 3.
Are you sure?
Something like that. Yeah. Okay.
Look at yours.
Oh, that one? That should be 4 or 5.
What the?
Right?
Oh,
4
that's
equations,
why?
Yeah, 5 on.
Oh.
Alright, so top one should be 1, 0, 1, 0, 0. Second one should be 0, 1, 0, 1, 0. Third one should be 1, 0, 0, 0, 0. And then the last one should be 0, 1, 0, 0, 1.
From being before the top here. Hits the
Oh.
There you go.
Okay, thanks.
I've heard about managers, something else going on.
I ain't got a boo-boo no more, y'all.
It is. Richard, is everything okay? Can you show me what's going on?
Sort of like this. Sometimes it turns off, but not that time.
Solomon laughing at me.
Do it enough times, it'll turn off eventually.
You ain't hear me too.
Are you perhaps potentially knocking one of your batteries loose when you do
I
that?
don't think so, I'm pretty sure those are meant to be held in pretty tight, right?
I mean, if you can seem like you're knocking
Look at
it
him.
kind of fine.
Okay, you pulled an arrow.
The sexual harassment.
Here, this is what you gotta do. There it is.
X plus 2 over X equal to 1.
I don't think I'm his type.
No.
Yeah.
Yeah, it is.
Greg, you can split up the numerator.
Okay, are we supposed to be doing this or?
You already have the domain restriction that X can be 0 from the other one, right? So, alright, we have our lovely graph that seems to be accurate based on people's graphing calculators. That was up Xavier.
I was just trying to think of what area we were going for, but I think we have a balance.
Yeah, 0 to 1. So I am rotating. Let's put 1 right there. That thing about the x-axis. So this little shape's coming out of the board, rotating around, coming into the board below, and then back around. So it's time to remember your chapter 6. Is this disc washer, disc and washer method, or is this method of cylindrical shells? Discs and washers. All right, what's our trial area? What's the area of a circle? Pi r squared. What's our radius of our little disc gonna be?
The Adam sheet.
Yeah, that thing. So pi 3 over x plus 2 times x plus 1 squared.
Yes.
And I want to integrate this thing from where to where? 0 to 1. So volume is equal to integral 0 to 1 pi 3 over x plus 2 x plus 1 squared dx. Let's handle constants and stuff. 3 squared, I believe, is 9. And we got a pi going on, so I'm going to pull out 9 pi. And then down the denominator, I'm going to have x plus 2 squared times x plus 1 squared. And we're integrating a rational function. What's the degree of your denominator? 4. We got 2 linear factors, but each one of them is squared. So it's going to be 4. And then what's the degree of the numerator? 0. So degree of the denominator is bigger than the numerator. It's partial fraction time. We have 1 over x plus 2 squared, x plus 1 squared. So these are linear factors, but they are repeated linear factors. So above each we're going to place constants, but I do need to account for each possibility of one of them being over x plus 2 and the other one potentially being over x plus 2 squared.
Sorry, but could you repeat what makes something a repeatable factor one more time?
The exponent being something other than 1.
Okay.
Right, if we were to get rid of all the exponents in my denominator, here would be x plus 2 times x plus 2 times x plus 1 times x plus 1. So it's a linear factor of x plus 2 and x plus 1. They're both repeated twice.
Okay, gotcha.
A over x plus 2 plus b over x plus 2 squared plus c over x plus 1 plus d over x plus 1 squared. Clear your denominators. We got 1 equals a x plus 2 x plus 1 squared plus b x plus 1 squared plus c x plus 2 squared x plus 1 plus d x plus 2 squared.
How did you like figure out how, what goes with what?
By canceling stuff. And I'm multiplying by x squared plus, or x plus 2 squared times x plus 1 squared.
Yeah.
I got x plus 2 here. So one of the x plus 2's are gonna cancel. I'm left with 1, nothing's happening to the x plus 1's. And the same thing here, the x plus 2's are both gonna cancel. No, just x plus 1 squared. And it's time for the funnest part of this. Right now,
Funnest.
multiplying all of this out and recombining, get your coefficients. That's something fun. Because this is going to be algebra, I'm going to breeze through this a little bit. So get ready.
It just keeps going.
This gotta be a prank.
X cubed.
This gotta be a prank, honey.
If this were a complex analysis class, guessing 2 pi I is not that bad of a guess. Let's see, 5,
This a prank.
8. And then last step.
Oh, Lord.
Cube.
Oh, hell no. Oh, hell no. I'm
Okay.
gonna catch a damn cramp.
Oh, wait, no, this is gotta be squared.
Lord have mercy. That don't make no sense. Look, y'all.
Yeah, I think this is great. When I said I wanted to just breeze through it, because it's just a bunch of foiling. Right. Does either do this or be like, hey, take 10 minutes to foil this out. Which one do you prefer?
Probably that.
This. Mine are equate like coefficients. So over here on the left, x cubed is 0. And we have x cubed here is a. X cubed here is c. And that's it for x cubed. X squared now over here on the left, coefficient 0. We got 4a, b, (5c) and d. Now we have x, which is 0, 5a. It's done 2b. C and 4D. 4D? Fourth dimension? Movies. Now instead of being just 3D, there's 3D and the shapes and
And you can spray with water.
Really?
I've seen verses where you like,
I definitely want to go to this one. And then last one, constants, we got 1 is 2a plus b plus 4c plus 4d. Alright, you have your linear system. I don't super care how you solve this linear system as long as whatever you do is technically correct. I think my recommendation here is going to be using your calculator.
Mm-hmm.
how many equations?
Yeah, 4 equations, 4 unknowns. So if you're using your matrix methods, you want to RREF this thing. 1, 0, 1, 0, 0. 4, 1, 5, 1. 5, 2, 8, 4. 2, 1, 4, 4.
You didn't plan
Am I gonna do this thing? Hell no. Ain't no shot. I'm doing that.
-2, 1, -2.
What do you get?
-2, 1, -2, 1.
I got 2, 1, -2, 1.
Oh, wait, no, that's 2, 1, -1. Sorry.
So it's 2, 1, -2, 1.
That's what the queen got.
That's good, because that's what my notes got.
Okay.
That's what the queen got.
A is 2,
That's what the queen got.
B is 1, C is negative 2, D is 1.
So this is a good one somewhere? No? To cancel for 0?
I don't have a negative 1 in my
I'm
notes.
just saying. I know with calculators, the calculator's probably right, but
Remember, it's A and C, so it's 2 and negative 2 up top.
oh, that's why they can't see.
Mm-hmm.
I see.
Now over here we got 9 pi,
Exactly that, exactly that.
integral 0 to 1 of 2 over x plus 2 plus 1 over x plus 2 squared plus negative 2, so minus 2. X plus 1, yeah, x plus 1.
Mm-hmm.
Plus 1 over x plus 1 squared. Alright, this is the thing that we need to integrate. How are you going to integrate this term?
Take out the 2.
You can take out the 2 for sure. But then we got 1 over x plus 2.
That's just natural log or something.
Yeah, it's going to be natural log. Think U substitution.
Mm-hmm.
Then we got this one, 1 over x plus 2 quantity squared. How are you going to do that one? U sub again, but instead of getting a natural log, you're going to get the thing that we kind of erased earlier of the negative 1 over x. Right? You're going to treat this as a negative exponent with U sub. You're going to get u to the negative 2, you raise it by 1 and you divide. How are you going to do this one?
Take out 2.
Take out 2, okay. And then what else?
Natural log.
Get a natural log, do a u sub again. And then how you going to do this one?
Same old pen.
No, that was x squared plus 1. No parentheses being squared here. This is u sub again. Yeah, this is all u sub every single one. It'd be what, 9 pi 2 natural log x plus 2. Oh, nope, minus 1 over x plus 2. Yeah. Yeah.
Mm-hmm.
Minus 2 natural log x plus 1. And then minus 1 over x plus 1. And then you do some plugging in. Of which I'm going to leave that in people's...
Wait, why that's negative?
Which one?
1 over x plus 2?
This one?
Yeah.
Remember your u sub, right? We have this thing, right? U is x plus 2, du is dx. That should look like a 2. Right, so that's going to become 1 over u squared du, right? Or u to the negative 2 du. And so raise the power by 1 to negative 1, right? And then divide by that negative 1. 1 divided by negative 1 is negative 1.
Negative 1.
And we get negative u to the negative 1.
Oh. You got me. You got me there. The queen was annoying.
Granted, it's my job to explain,
Yeah.
you know, more often than not.
The queen ain't know that one.
And I suppose this does bring up a worthy mention, because we're definitely not gonna have time for the very goofy, and quite frankly, very difficult one over there. Which is, don't forget about your early integration techniques. Don't forget about USUB, don't forget about direct integration. Let's briefly mention something about this and then move on to the case stuff. How on earth do you manage this, because your degrees are now equal? Yeah, Xavier.
I was gonna ask about your, so what do you
This and then move on to the case stuff. How on earth do you manage this, because your degrees are now equal? Yeah, Xavier.
I was gonna ask about your, so what do you